Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant. And a huge hello to all you students at Ishik Boys High School, especially Mr. Jager's class. We're really glad you're tuning in for this deep dive. Today we're tackling electric force and this really fundamental law called Coulomb's law. Our goal, to connect what you're learning in class with stuff you see, well, maybe not see, but stuff that happens all around you, make physics feel a bit more real.
Exactly. It's all about seeing how these ideas, these forces, explain things. Like, why does a sock cling fresh out of the dryer? Or even how atoms stick together.
Okay, so let's get into it. We talked about forces back in chapter 4, pushes and pulls, that change motion. But electric force, what makes it electric?
Good question. It's specifically the force between objects that have an electric charge. That's the key. It's the force making them either attract, pull together, or repel, push apart.
Right. Like the balloon experiments. I bet everyone's done that. That's in section 17.1 in your book, right? Rub a balloon on your hair, and suddenly it sticks to the wall or makes your hair stand up. That is electric force, isn't it?
That's exactly it. Those simple experiments show the core idea perfectly. You get attraction between opposite charges.
Yeah.
So if the balloon gets one type of charge and your hair gets the opposite, they pull towards each other.
Okay.
But if you charge two balloons the same way, maybe rub them both with wool, they'll have the same charge. Then try bringing them close together.
They push each other away. Repulsion.
Exactly. Like charges repel, opposite charges attract. That's sort of rule number 1 for electric force.
Okay, so charges attract or repel. But what decides how strong that push or pull is? Like if you rub the balloon for ages, does it get stronger? Does how close you bring it matter?
Yes, definitely both. You've hit the nail on the head. The amount of charge matters. More rubbing might mean more charge, so maybe a stronger force. And distance is huge. Think about it. When the balloon is far from your hair, nothing much happens.
Right.
But bring it closer, and suddenly your hair starts reaching for it. So distance and the amount of charge are the big factors.
And this is where Charles Coulomb comes in back in the 1780s. He wasn't just satisfied with saying closer is stronger. He wanted numbers. How on earth did he measure such a tiny force back then?
It was really clever. He used something called a torsion balance. Picture like a tiny dumbbell, two little spheres on a rod hanging from a super thin thread like a silk fiber.
Okay.
Then he'd bring another charged object near one of the spheres. The electric push or pull would make the rod twist. By measuring how much it twisted, he could figure out the exact strength of the force. Pretty ingenious.
Wow. Okay, so what did his measurements actually show? What were the relationships he found?
He found two really key things. First, about the amount of charge. The force is directly proportional to the product of the two charges. So Q1 times Q2.
Product. So multiply them. What does that mean practically?
Right. So let's say you double the charge on one object, keeping the other the same. The force doubles. Simple enough. But, and this is cool, if you double the charge on both objects, the force doesn't just double again. It goes up by 4 times. Because you're doubling Q1 and doubling Q2, so the product is 4 times bigger.
4 times. Okay, that ramps up quickly. And what about the distance?
That was maybe even more surprising. He found the force is inversely proportional to the square of the distance between them.
Inverse square. Okay, break that down. Inverse means as distance goes up, force goes down.
Right, but the square part is crucial. It means if you double the distance, the force doesn't just get cut in half. It drops to 1/4 of what it was. 2 squared is 4, so 1/4.
Oh.
And flip that around. If you have the distance, make them twice as close.
Don't tell me. 4 times stronger.
Exactly. The force jumps up by a factor of 4. It gets incredibly strong when things are close and drops off really fast as they move apart. This inverse square thing is super important in physics.
So these discoveries, they lead to Coulomb's law, the formula. Electric equals Kc times Q1 Q2 over R squared. Let's just quickly touch on what those symbols mean, not for solving problems, but just understanding the idea.
Sure. Electric is just the electric force we're measuring. Q1 and Q2 are the amounts of charge on object 1 and object 2, how much charge they're carrying.
Okay.
R is the distance between them, center to center usually. And Kc is just a constant, the Coulomb constant. It's a fixed number, about 8.99 times 10 to the 9. That makes the units work out, right? So the force comes out in newtons when charge is in coulombs and distance is in meters.
So the formula basically packs Coulomb's 2 big discoveries into one equation. More charge means more force, less distance means way more force.
That's the essence of it. And one more important thing, force is a vector.
Right. Direction matters.
Totally. It has magnitude, how strong a direction. The electric force always acts along the line, connecting the two charges, either pulling them together or pushing them apart along that line. Oh, and technically, the law works perfectly for point charges, like imaginary dots of charge, or for perfectly spherical charges, where r is the distance between their centers.
Now, we've all learned about gravity. It also pulls things together. How does this electric force stack up against gravity? Are they similar?
That's a great comparison to make. They have interesting similarities, yeah.
Yeah.
Both are field forces. They work across empty space. Earth pulls on the moon without a rope, right? Charges push or pull without touching.
Okay, acting at a distance. Got it.
And both follow that inverse square law with distance. Strength drops off as 1 over r squared for both gravity and electric force.
But they must be different too. Gravity only pulls, right? It's always attractive.
Exactly. That's a huge difference. Gravity is always attractive because mass, which causes gravity, is always positive, as far as we know. But electric charge comes in positive and negative, so you get attraction and repulsion.
And what about strength? You said the balloon can lift hair against Earth's gravity. That sounds like electric force might be stronger.
Stronger is an understatement.
Yeah.
It's vastly, unbelievably stronger. That little bit of static charge on a balloon overcoming the gravitational pull of the entire planet on a strand of hair tells you something. At the atomic level, like between a proton and an electron in a hydrogen atom, the electric force is something like 10 to the power of 39 times stronger than the gravitational force between them.
Yeah.
It's just staggeringly dominant on that scale.
Okay, hold on. If it's that much stronger, why isn't everything just constantly flying apart or sticking together? Why does gravity seem to run the show for planets and stars and us? Why don't we feel that huge electric force all the time?
Excellent question. It comes down to balance. Most matter, most everyday objects, are electrically neutral overall. They contain enormous numbers of positive charges, protons and nuclei, and negative charges, electrons, but they usually contain equal amounts.
Ah, so they cancel out.
Exactly. The attractive and repulsive forces within the object and between it and other objects largely balance out on a large scale. Gravity, on the other hand, only adds up. Every bit of mass pulls on every other bit. So for big things like planets, gravity wins out because it's always attractive and adds up, while the electric forces are mostly neutralized.
That makes sense. Okay, so far we've mostly talked about just two charges interacting. What happens if you have, like, 3 or 4, or a whole bunch of charges all near each other?
Right. The real world is usually more complicated than just two charges. That's where we use something called the superposition principle.
Sounds complex.
It sounds fancy, but the idea is actually pretty straightforward. It just means that if you want to find the total electric force on one specific charge, you just figure out the force exerted on it by each of the other charges individually. Calculate the force from charge A, then the force from charge B, then from charge C, and so on.
And then just add them all up.
Almost. You add them up as vectors. Remember, direction matters. So you find each individual force, vector, magnitude, and direction, and then you do a vector sum, like adding arrows head to tail, basically, just like you did with other forces in Chapter 4.
Okay, so is vector addition, again, we don't need to do the actual addition here, but the concept is find each force, then add them considering their directions.
You got it. That gives you the net, or resultant, electric force on your target charge.
And sometimes, I guess, all those pushes and pulls might perfectly balance out.
Exactly. That leads to the idea of equilibrium in electrostatics. A charge is in equilibrium if the net electric force on it, the vector sum of all the forces from all the other charges, is 0.
So it's not being pushed or pulled overall?
Right. All the forces acting on it cancel each other out perfectly. Which ties right back to Newton's first law, doesn't it? If the net force is 0, an object at rest stays at rest. So if a charge is placed at an equilibrium point and isn't moving, it'll just sit there.
Finding that spot involves setting the forces in opposite directions equal to each other, conceptually speaking.
Conceptually, yes. You're looking for that sweet spot where the push from one side exactly balances the pull from the other side, or however the forces combine to equal 0. Again, the idea is balance, not the specific calculation today.
Okay, great. So let's wrap up what we covered. We looked at electric force, the push or pull between charged objects. We saw it can be attractive or repulsive. We talked about Charles Coulomb and his amazing work figuring out how force changes with charge amount and distance, leading to Coulomb's law.
Especially that inverse square relationship with distance and force being proportional to the product of the charges.
We also compared electric force to gravity, similar in some ways, like being field forces and inverse square laws, but vastly different in strength and the fact electric force can repel.
And we touched on how to handle multiple charges using the superposition principle, basically adding up the individual force vectors.
Yeah.
And what equilibrium means, zero net force.
All right, so here's a question to think about, connecting back to that strength difference. We said electric force is incredibly strong and atoms are full of positive and negative charges. So why don't we usually feel strong electric effects from everyday objects? Think about that cancellation idea we mentioned.
It's a good one to ponder. Really makes you appreciate the balance within matter.
Yeah.
Definitely. Well, that's our deep dive for today. Thanks for joining us.
Stay in contact with your physics teacher. Stay creative.